Hi everyone. We are going to pick up on our conversation about logarithmic functions, which I introduced last week, and we are going to talk today about transformations of logarithmic functions. So these work the same as transformations of any other type of function. So it is useful to keep in mind that when you have y equals f of x, if that's your base function, and that's going to transform to y equals a f of b times x minus h plus k. And if we can write our new transformed function in this format, then we can clearly see the values of a, b, h, and k, and those will tell us about our stretches, our reflections, and our translations. Okay. Now with a logarithmic function, the base function is y equals log base c of x. So that c value can change. We saw in our last class we had a base of 2, we had a base of 10. So that c value, just like in an exponential function, can change. It's not considered a parameter that would transform the function. But if we transformed this, what this would look like is y equals a times the function. So the function is log base c of x. Instead of x, though, I'm going to put a set of brackets, and in that set of brackets has to go whatever is in here. So that's b times x minus h, and then plus k at the end. Okay, and then we will know, just like in all of our other transformations, a, for example, is the vertical stretch factor, or its absolute value is the vertical stretch factor, and then it could have a reflection as well, and so on and so forth. Okay, so also good to keep in mind that the mapping notation would work exactly the same way. The point xy will map to 1 over bx plus h, ay plus k. Okay, so we are going to start by looking at a simple transformation. We've got the graph of y equals log x. This is going to be our base function. Using your knowledge of transformations, sketch y equals log of x plus 4 plus 2. So one thing I want to remind you of is that when there's no base written in, that is the common logarithm, and the base is 10. Okay? So what I'm going to do is I'm going to make a little table of values just to get a couple points, and I will have x and log x. So this would be our y value, log base 10 of x. Okay. Now the nice numbers that are going to give my when I evaluate the logarithm, nice whole numbers to put in for x would be powers of 10. So I'm going to start with 10 to the negative 1, which is 1/10. So if I stick a 10 to the negative 1 in here, essentially what I'm saying is 10 to the what equals 10 to the negative 1. And that answer, if you can write the x value as a power of 10, will always just be the exponent. This is going to be negative 1. Okay. If I put in 10 to the 0, which is equal to 1, I'm saying log base 10 of 10 to the 0, 10 to the what equals 10 to the 0. That is 0. And 10 to the 1, which is 10, I would be saying 10 to the what equals 10 to the 1, and that answer is 1. So when you can input your x values as powers of the base, evaluating the logarithm becomes quite quick. Okay, so I am very quickly just going to sketch this. Looks like I have some stuff on there. Okay, I'll erase that, and I'll put in these 3 points. So I have 1/10 negative 1. So that's very close to the y-axis over here. And then I have the point 1, 0, which is here. And I have the point 10, 1, which is here. Okay. And I'm going to graph this. In this case, the y-axis is my vertical asymptote. Okay. And that's the line x equals 0. Okay, so we talked last class as well about the fact that logarithmic functions are inverses of exponential functions. So if an exponential function has a horizontal asymptote, a logarithmic function will have a vertical asymptote. Okay, so now we're going to take a look at this transformed function. And if we think about the parameters a, b, h, and k, I don't see anything in there about the a and b value. So we can assume that those are both 1, which is nice because that means we don't have any stretches or reflections. All that's happening here is we have translations. So we are moving, it looks like h is -4, so 4 left and 2 up. K is 2. So what I'm going to do is take all of these points that I've just graphed and I'm going to move them 4 left, 1, 2, 3, 4, and 2 up. So this point I'm going 4 left, 2 up. I'm trying to get really close to the sort of 1/10 mark, but it's hard to do. This point 1, 0 is going to move 4 left and 2 up to there. And then 10, 1 will move 4 left, so that's to 6, and 2 up from 1 is at 3. So here are my points. And then on this end, it's going to shoot down along here, right? So that vertical asymptote will also move 4 left, and this is the line x equals -4. Okay, so that's part A. What is the equation of the asymptotes? That would be x equals -4. Okay, domain and range. So the domain, all of the x values are to the right of -4. And because that's an asymptote, x will never actually hit -4. So for our domain, x is greater than -4. And for the range, in a logarithmic function, y can be anything. Okay, so x and y intercept. So in the base function, the x-axis, the y-axis, the line x equals 0 is an asymptote. So you're actually not going to have any y-intercepts because it's never going to hit the y-axis. But if you transform it and move it around, you might end up seeing that there are some intercepts. Now in this case, algebraically, what we would do to get an x-intercept is set the y value equal to 0. So for the x-intercept, we would have 0 equals log of x plus 4 plus 2, and we would have to solve that. This one actually we could solve. So if we move the 2 over, -2 equals log base 10 of x plus 4. And then we switch into exponential form. The base of our exponent, or our power rather, is 10. The exponent is the value of the logarithm, so that's -2, and that's equal to x plus 4. Okay, and 10 to the -2 is 100th. So that is, 100th is 0.01 equals x plus 4. And then you can subtract 4 from both sides, and 0.01 minus 4 is -3.99. Okay, so actually that one you could do algebraically. In this case, for the y-intercept, right? For a y-intercept, that's when the x value is 0. So this one you have to do on your calculator because that value is going to be log, whoops, my pen cut out, there we go, of 0 plus 4 plus 2. And you can only evaluate the log of 4 on your calculator. You could also just graph this and find your intercepts using the graph. That's totally fine too. This is about 2.60. Okay, so that's the y-intercept right there. It's 2.60. Okay. All right, let's look at another example. So here we have sketched the graph of y equals -2 log base 5 of x plus 5. Okay, so a couple of things that would be helpful to do here. One of them, be really aware of what your base function is. Okay, so the base function is always y equals log base c of x. So the base in this case is 5, so the base function is y equals log base 5 of x. And we're applying transformations to this function, okay? Now, the a value is -2. Okay, so what that tells us is that there is a vertical stretch factor of 2, and because a is negative, there is also a reflection in the x-axis. Okay, and then we also have some translations. So it looks like the h value is -5. So we're moving 5 left, and k is 4, so 4 up. Okay, now when I'm graphing these, I always try to keep in mind where the vertical asymptote is going to move to. So the vertical asymptote is always your h value. It's the number of units you're moving left or right. So I'm actually going to put that in. Okay, and this is not a requirement, but I would suggest if you're doing this by hand, doing this as well, in that I'm going to do this in another color. I'm going to graph the base function as well. So I'm going to make a little table of values for this function, log base 5 of x. Okay, and the nice numbers to put in here would be powers of 5, okay, because then the value of the logarithm is just the exponent on the 5. So I'm going to put in 5 to the -1, which is 1/5. I'm going to put in 5 to the 0 rather, which is 1, and 5 to the 1 is 5. So those are my x values. My y values will be -1, 0, and 1. Whoops. Just erase that. There we go. Okay, so I'm going to plot that, and I'll do that in red. So my first point is 1/5, -1. So that's about here. And then 1, 0, and then 5, 1. So that's here. Okay, so there's my base function. Okay, now when I am drawing the transformed function, for this type of thing, it is a little tricky to do all of the transformations just looking at the base function. So it's totally fine if you want to use mapping notation and just plot a couple of points, okay? We are aware of the transformations, so we should be able to do the mapping notation. So in this case, I'll switch colors again. Whoops. The point x, y will move to the point, okay, so b is 1, so 1/1 is just 1x, and then -5, comma, and then ay plus k, so -2y. Plus 4. Okay, and you could take these 3 points that we have and map one to the other. Oh, I'm running out of room here. Okay, I'm not using my smartboard, so I can't just extend the page. Okay, so maybe I'll do this over here. Well, I'll see if I can squish it in. The point 1/5, you can think of that as 0.2. That might be an easier way of doing it. And then -1 will be mapped to 0.2 minus 5 is -4.8. And then this would be -2 times -1 is 2 plus 4 is 6. The point 1, 0 will be mapped to 1 minus 5 is negative 4. And then negative 2 times 0 is 0, plus 4 is 4. Okay? And then the point 5, 1 will be mapped to 5 minus 5 is 0. And negative 2 times 1 is negative 2 plus 4 is 2. Okay? And then to get the transformed function, I can plot these 3 points. So the first one is negative 4.86, so that's about here. And the second one is negative 4.4, that's here. And then 0, 2, that's here. So this is going to kind of look like this. Okay? So doing the stretches with these logarithmic functions can be a little tricky, so if you want to use mapping notation, totally cool. You can also graph this on your calculator just to get a sense of what it's going to look like, and do it that way. Okay, equation of the asymptote is at x equals negative 5. The domain x is greater than negative 5, and the range is y is an element of the real numbers. Okay, now in this case, we can actually see the y-intercept. The y-intercept is at 2, and we actually got that out of our mapping notation, or our mapping. We can see right here, this is the y-intercept. Okay, so this is at 2. To get the x-intercept, again, the x-intercept is when y equals 0. So if you set 0 equal to the function, negative 2 log base 5 of x plus 5 plus 4, and then essentially what we want to do to solve this is isolate the log, and then you can switch into exponential form. So I'm going to start by subtracting 4 from both sides. Okay, and then I'll divide by negative 2, so I get negative 4 over negative 2 is 2 equals log base 5 of x plus 5. And now I can switch forms into exponential form. So I'm just going to continue over here because I'm really running out of room. So the base of my power will be 5. The exponent is 2, and that's equal to x plus 5. Okay, and that's 25 equals x plus 5. So subtract 5 from both sides. X equals 20. That is your x-intercept. Okay. Let's try another one. Okay, so here we've got y equals 3 log base 2 of negative x plus 6. So a couple things to think about. Number 1, the base function in this case would be y equals log base 2 to the x. Okay, and I personally really like just thinking about a few points. And just a nice hint, put in powers of 2 for your x value. So 2 to the negative 1, that's a half. The value of that logarithm is negative 1. 2 to the 0 is 1. The value of the logarithm will be 0. It's the exponent on 2. 2 to the 1 is 2. That'll be 1. And maybe let's do one more. 2 squared is 4. And the exponent on 2 there is 2. Okay? So I'm actually, I think, going to plot that. Maybe I'll do that one in red so that we know the difference. So I'll just make sure, okay, this stuff is in red. Okay? So I've got the point a half negative 1. That's here. And then 1, 0. 2, 1. 4, 2. Whoops. Sorry. I did 4, 1. There we go. And in fact, the next point, 2 cubed, is 8. So that would be 8, 3. So you could put another one in there too if you want. and there is my base function. Okay, so that's the base. Now, to sketch the graph of y equals 3 log 2 of negative 2x plus 6, please, please, please remember that this has to be in factored form to be able to see the horizontal translation. So please rewrite it first as y equals 3 log base 2 of negative 2 times x minus 3. Okay, factor out that negative 2. So what we're considering here is essentially a vertical stretch factor of 3, horizontal stretch factor of 1/2. It's the reciprocal of b, or the absolute value of the reciprocal of b, and also a horizontal reflection. And then we're moving 3 right. Okay, so if you wanted to do some mapping, the point xy is going to map to negative 1/2 x plus 3 and then 3y. Okay, now I'm really running out of room here, and I can't extend the page because I'm not on my smartboard, but I think what I'll do is try and do the mapping down here. This will move to negative 1/2 x plus 3 and 3y. Let's see if I can squish it in. So the first point was 1/2 negative 1. And that's going to become negative 1/2 times 1/2 is negative 1/4 plus 3. 3 minus 1/4, that's 2.75. And then 3 times negative 1, that's 3y. Sorry, it's really squishy. That's negative 3. Okay, and then the next point is 1, 0. So that's going to be negative 1/2 times 1 is negative 1/2 plus 3. 3 minus 1/2 is 2.5. And then 3 times 0 is 0. So that's quite nice. 2, 1. Negative 1/2 times 2 is negative 1 plus 3 is 2. And then 3 times 1 is 3. And we'll do one more. 4, 2. So negative 1/2 times 4 is negative 2 plus 3 is 1. Negative 2 plus 3 is 1. And then this will become 6. Okay, so I am now going to plot these points. So I'll start with 2.75, negative 3. So that's about here. Okay, and then the next one is 2.50. That's there. 2, 3. That is there. And then 1, 6 is there. Okay, so here is my graph. Okay, and this, by the way, 3, which is the h value, is my vertical asymptote. Okay, so equation of any asymptotes, that is x equals 3. Domain and range. So in this case with the domain, because there is a horizontal reflection, the x values are going to be less than 3 instead of greater than 3. So that's our domain. And our range is x is an element of the real numbers. Okay, now the x-intercept we can see. That's at 2.50. So the x-intercept would be 2.5. Just in the interest of time, with this particular function, I am going to get you guys to graph it and figure out the y-intercept. So you would go like second calc value, enter in an x value of 0. But actually, having said that, it's not that hard. When you're finding a y-intercept, remember that x equals 0. So you can just plug x equals 0 into the function 3 log 2 of, I'll just plug it in the original, negative 2 times 0 plus 6, right? So if essentially it's going to be 3 log base 2 of 6. And that is approximately 7.75. Okay, I've done that on a calculator, so actually that's right there. All right? Okay. Okay, so we are going to look now at some graphs and try and figure out if we can determine the transformations. Okay? So looking at this first one, this one, there's actually 2 ways of doing it. And we're going to actually come back to this example tomorrow when we look at laws of logarithms. So I think probably the most obvious is that if you compare the red graph to the blue graph, everything's been moved up 1, right? So all the y values have gone 1 up. So that's a vertical translation up 1. So the new function would be log base 4 of x plus 1, okay? There is actually another way of seeing this though, and you can also see it as a horizontal stretch. And essentially what's happened is all of the x values have stretched by 1/4. So the 0.10 has moved to 1/4 0. The 0.41 has moved to 1 1. Okay, so if there is a vertical stretch of 1/4, that means the b value is 4. It's the reciprocal. Oh, sorry, this should be a 4. Okay, now tomorrow, I should say y equals, we are going to look at why these are equivalent to one another. Okay, okay, let's look at this next one. We've got the same base function, y equals log base 4 of x. And right away, I can tell that there has been a vertical reflection, okay, because the orientation of the function has flipped over the x-axis. Okay, so that has for sure taken place. If we sort of flipped it back, right, imagine before the reflection, because there's something else going on as well, right? So this is my invariant point right here, which makes sense. On when you're flipping over the x-axis, anything on the x-axis isn't going to move, but I'm really going to focus in on this point. This is a distance of 1 away from the x-axis, and then that has moved to 3 away from the x-axis. So there has been a vertical stretch of 3. Okay, so there's 2 things going on. There is a vertical stretch of 3, and there's a reflection in the x-axis, a vertical reflection. So this will be y equals -3 log base 4 of x. Okay, the a value will affect both the vertical stretch and the vertical reflection. Okay, and we are going to finish off today with one application question. So let's take a look. Scientists found that the relationship between the number f of flower species that a butterfly feeds on and the number b of butterflies observed can be modeled by the function f equals -2.641 plus 8.958 log b. Okay, so f is the number of flower species, b is the actual number of butterflies. Okay, and what we want to know here is predict the number of butterfly observations in the region with 25 flower species. So what we know here, this 25, whoops, oh, I have to put the pen back on. There we go. This 25 is our f value. Okay, so what we're going to do is sub in that for f and then try and solve for b. So we are going to have 25 equals -2.641 plus 8.958 log b. Okay, now, what you can do here is graph this is equal to y1, and this is equal to y2, and then get the intersection point. And you're looking for the x value. So we have done that a lot. I'm not going to go through that right now. What I actually want to do, though, is show you how you can also solve this one algebraically, because that could be an expectation too. And the key with solving algebraically is before you do anything, you have to isolate the log. So I really want this piece to be isolated. So I'm going to start by adding adding 2.641 to both sides. So if I add 2.641 to the left side, I'm going to have 27.641. And on the right side, that will make 0 equals 8.958 log b. Okay, now I can divide both sides by 8.958, because ultimately I want to isolate the logarithm. And if you want, you could leave that as a fraction, or I'm just going to get a decimal approximation. So I'm just doing this off to the side. 27.641 divided by 8.958, and that is 3.0856. And it keeps going, but I'm just going to stop there. Equals log b. Okay. Now remember that when there's no base written in, the base is 10. Once you have isolated the logarithm, switch forms. Switch to exponential form, and you should be able to figure out the value of b. Okay. So in exponential form, the base of the log is the base of the exponent, or the power rather. So the base is 10. The exponent is the value of the logarithm. So that's 3.08562, and it keeps going. And if you have that number in your calculator, don't erase it. Use your answer button, and then you can just put it right back in. And that's equal to b. So to get the value of b, we need to go on our calculator, 10 to the power of 3.065, or 3.08562, etc. So I'm going to do that quickly. And I'm going to use my answer button so I keep all those decimal points. And to the nearest butterfly, I'm getting that b, equals 1,218. Okay, now if you solve that graphically, no problem. The one challenge with solving graphically in this case is it can be a little tricky at first when you're getting used to these types of functions to determine your window settings. Okay, so, and if you think about it, you would have to have an X max big enough on your window settings to get to 1,218. So that can take quite a bit of time. Sometimes it's faster to solve these algebraically. So I am going to end there for today, and tomorrow we will pick up and talk about log laws, which I referred to a little bit earlier.